chemistry students. You are welcome to the second semester chemistry course General and Inorganic Chemistry. Unit 3 of this course is on the covalent bond. So far in this course we have learnt about atomic structure, periodic classification and the ionic bond. Now we move further and try to learn about the covalent bond. The current chapter, that is chapter 3.1, is on the Lewis dot structures and arrangement of electrons in molecules. The instructor for this chapter is Dr. P. Sharada, selection grade lecturer in chemistry, St. Joseph's College for Women, Autonomous, Visakhapatnam. Learning outcomes. By the end of this chapter, the learner would be able to comprehend the meaning of covalent bond, draw Lewis structures and depict electron distribution in molecules, represent single and multiple bonds along with canonical forms of covalent molecules through Lewis structures, and also compute formal charge of atoms in covalent molecules. Now let us see what are the contents of this chapter. The contents of this chapter are covalent bond, introduction to Lewis structures, that is representing a covalent bond through Lewis structure, steps to draw Lewis structures of some indicative molecules, and formal charge. Let us go to the first part of the chapter on the covalent bond. As we already know, as we have already learnt in our previous classes, the covalent bonds are formed by the sharing of electron pairs. It is clearly shown here, wherein you are having two atoms, atom 1 and atom 2. Atom 1 is having 7 electrons in its valence shell. Atom 2 is also having 7 electrons in its valence shell. For the sake of stability, they want an octet, that is octet configuration is associated with extra stability. So, in order to gain stability, atom 1 and atom 2 contribute 1 electron each towards the covalent bond, and so atom 1 and 2 together form a covalent molecule by the sharing of 1 pair of electrons which are contributed by both atom 1 and atom 2. Now let us see the salient features of a covalent bond. Covalent bonds are formed by sharing of electron pairs. Generally, covalent bonds are formed between non-metal atoms or a non-metal and a metalloid. That is to say, non-metals that are deficient of octet configuration, that are having less than 8 electrons in their valence shell, they form homonuclear molecules as well as heteronuclear molecules by the sharing of pairs of electrons. Each atom contributes 1 electron to the pair, that is both the atoms contribute 1 electron each. Of course, we have also learnt about the coordinate covalent bond, where one single atom contributes both the electrons, and the one that gives both the electrons is called as the donor, and the one that accepts both the electrons is called as the acceptor. Nevertheless, irrespective of which atom is contributing both the electrons, the resultant pair of electrons are shared by both the bonded atoms. So, covalent bond simply means sharing of electron pairs. Generally, if it is not a coordinate covalent bond, each of the bonded atoms contribute 1 electron towards the bond, and combining atoms generally attain noble gas configuration in the valence shell through the process of sharing of electron pairs. Then if they share one pair of electrons, they form a single bond. If they share two pairs of electrons, a double bond is formed. And in case three pairs of electrons are shared, you have the nitrogen as the example, which share the two nitrogen atoms form the homonuclear diatomic molecule, and the two atoms share three pairs of electrons, resulting in the formation of a triple bond. You can see here the carbon dioxide molecule. There is a double bond between carbon and the two oxygen atoms. You can see here there is a double bond. Double bond means two pairs of electrons. That is why between carbon and oxygen you can see four dots. Four dots means two pairs of electrons. Similarly, between this carbon and oxygen also you have four dots, means two pairs of electrons are shared between the two bonded atoms. So, what have we learnt? Covalent bond formed by the sharing of electron pairs. Each atom generally contributes one electron towards the bond. The purpose is to attain the noble gas configuration or an octet of electrons. If one pair of electrons are shared, it is a single bond. Two pairs are shared, double bond. Three pairs are shared, it becomes a triple bond. Now, let us learn about the Lewis dot structures. Lewis structures are used to depict how atoms share electrons when they form molecules. That is, how are the electrons shared between the bonded atoms when they form molecules. We know very well that it is the valence shell and the electrons in the valence shell that are involved in the bonding process. So, how are these valence electrons distributed around the atoms in the molecule is what you are trying to depict through the Lewis structures. Lewis structures showcase bonding in molecules and ions in terms of shared electron pairs and also in terms of the octet rule. The main focus is that every atom should get 8 electrons in its valence shell. Of course, there are exceptions where molecules get less than octet, where you have greater than octet also, but generally with the octet rule in the mind, the Lewis structures are drawn. Lewis structures do not show actual shape of the molecule. Lewis structures have nothing to do with the shape of the molecule. Simply, we arrange atoms in the molecule with maximum distance from one another, and then we try to distribute the electrons between the atoms in such a manner that every one of the outer atom gets an octet and the central atom also gets an octet or greater than an octet. There are certain rules to be followed while drawing the Lewis structures, but Lewis structures do not show the shape of the molecule, and you can see they help in understanding the properties of molecules. You can through the Lewis structures you can also predict some properties. You can say which one is having a lone pair of electrons, is it a Lewis acid or a Lewis base, things like that. They can be predicted. You know, the Lewis structures can be used for prediction in the properties of molecules. As I already told you, they show only the valence electrons. See, Lewis structures can be drawn for atoms, molecules and ions. Here you can see the Lewis dot diagrams for atoms. Hydrogen is having only one electron. See, H, and H is the symbol of hydrogen, one electron. Helium is having two electrons. See how the two electrons are drawn farther from one another. Lithium is having one valence electron. See, actually lithium configuration is 1s2, 2s1. But in Lewis structures, we don't show the penultimate shell or any shell other than the valence shell. So, only valence electrons are shown. Lithium is 2s1, beryllium is 2s2, boron is 2s2, 2p1, then 2s2, 2p2, like that. This is how the elements or the atoms are shown with their valence shell electrons through the Lewis structures. Next, let us see how the ions are shown. You can see here sulfur is having a, you can see S2P4 configuration, 3S2, 3P4 configuration. Suppose it is a sulfide. Sulfide is S2 minus, that is, apart from its 6 electrons, if it gains 2 more electrons, it becomes S minus 2. So, this is the Lewis dot structure for sulfur atom, 3s2, 3p4, and this is the Lewis dot structure for the sulfide ion after gaining 2 electrons. You can see here After gaining 2 electrons, see sulfur, and this is the sulfide. Aluminium, you can see 3 electrons. Aluminium is 3s2, 3p1. But what are you showing? You are showing Al3 plus, means after losing 3 electrons, absolutely no dots. Why no dots? Because all 3 electrons are lost in the process. So you can use Lewis dot structures to depict molecules. We have seen in the previous slide how molecules are depicted. You can use the Lewis dot structures to depict atoms and ions. Supposing you are depicting the CH4 molecule, you can see here carbon at the center, and there are 4 hydrogens surrounding the carbon, and you can see between the hydrogen and carbon there is a pair of electrons. Blue electron, if you think, belongs to hydrogen, the red electron belongs to the carbon, and this is how the Lewis structure of CH4 will be depicted. You can see the water molecule here. Water is having oxygen and 2 hydrogens. We know between hydrogen and oxygen there is 1 pair of electrons. Another hydrogen and oxygen there is another pair of electrons. Despite that, oxygen is still having 2 lone pairs of electrons. As we already said, by looking at the Lewis dot structures, we can roughly predict some of the properties of the atoms as well as the molecules. Single, triple and double bonds, how they are depicted, let us see. You can see I already told, if only 1 pair of electrons is shared, you get it like this. Hydrogen, between the 2 hydrogen atoms you are having a single bond. Between the 2 oxygen atoms you are having a double bond, that is 2 pairs of electrons are shown, and between the 2 nitrogen atoms you are having a triple bond, that is 3 pairs of electrons are shown. You can see here in this particular molecule, between hydrogen and oxygen there is a single bond, hence 1 pair of electrons. Between the 2 carbon atoms you are having a triple bond, hence 3 pairs of dots, and there is a double bond between the 2 carbon atoms here, hence you are having 2 pairs of dots over there. So that is how single, double and triple bonds are depicted in the Lewis structures. Next, let us see the steps or the rules to draw Lewis structures. Molecules with 1 central atom. In this video, we will discuss about writing the Lewis structures for molecules with 1 central atom only. Now, count the total number of valence electrons in the molecule. Total number of valence electrons in the molecule means we have to see the number of valence electrons for every atom in the molecule. For every atom in the molecule, count the number of valence electrons, add up, and then you will get the total number of valence electrons in the molecule. Compensate for charge. Compensate for charge means, supposing it is a CO3 2 minus, means you have to add the valence electrons of carbon, 3 oxygens, and also add 2 electrons to it. That is because the charge is -2. So first count the number of valence electrons in each of the bonded atoms, sum them up, that is add them up. After adding, compensate for the charge. For example, you are counting for NH4 plus, means after getting the total you have to subtract 1. You are counting for CO3 2 minus, that is after getting the total you have to add 2 more. So count the total number of valence electrons, compensate for the charge. For example, here I have given the example of CH4. We know that for carbon, what is the valence shell configuration of carbon? 2s2, 2p2. So how many valence electrons? Carbon is having 4 valence electrons. Apart from carbon, you are also having 4 hydrogens. Each hydrogen is having 1 valence electron, which means 4 from carbon and 4 from 4 hydrogens, which is equal to 8. So the total number of valence electrons in CH4 is 8. Look here, for CO3 2 minus, there is 1 carbon and 3 oxygens. Each carbon will contribute 4 electrons. Each of the oxygen, what is oxygen electron configuration? 2s2, 2p4, which means there are 6 valence electrons in each oxygen. You are having 3 such oxygens, which means 3 into 6. So 4 plus 3 into 6 plus 2. Why did I add 2? Why did I add 2? Because charge is 2 minus. That means you need to add 2 more electrons. So the sum total of valence electrons in CO3 2 minus is 24. Look here, for NH4 plus, there are 5 atoms, 1 nitrogen and 4 hydrogens. Each nitrogen, what is the valence shell configuration of nitrogen? 2s2, 2p3, means it is having 5 electrons. Each hydrogen will contribute 1 electron, which means there are 4 hydrogens. So 5 plus 4 is 9, and because it is having a plus 1 charge, you subtracted 1 here. So the total number of valence electrons is 8. So if you want to get the total number of valence electrons, you have to see what all atoms are there. Each one is having how many valence electrons, sum them up, compensate for the charge, then you will get the total number of valence electrons. Next step is identify the least electronegative element or the least electronegative atom. So that will be the central atom. That will be the central atom. Atom which is least electronegative will be considered as the central atom. And after that, draw a skeleton structure with the symbol of the least electronegative element at the center and connect other atoms to it with single bonds. Single bond means a pair of electrons. Why should you identify the least electronegative atom or the least electronegative element? That is the center. And after putting it at the center, surround it with the other atoms of other elements and connect the central atom with the outer atoms with one pair of electrons each with one single bond. For example, you can see the SO3 here. Sulfur is less electronegative than oxygen. So sulfur is considered as the central atom here. And you are taking SO3, no? Means there are 3 oxygens that are connected to sulfur with a single bond. Look here for NH4. NH4, nitrogen is taken as the central atom and nitrogen is connected to 4 hydrogens through 4 single bonds. Here, phosphorus is taken as a central atom. It is bonded to 5 chlorines through 5 pairs of electrons or 5 single bonds. Then let us see. Add electrons to outer atoms as dots such that each one gets an octet except hydrogen, which should get a pair only. Hydrogen can have only one pair. See, there is this rule you should never violate. This rule should never be violated. Means don't focus on the central atom at first. Focus only on the surrounding atoms or the outer atoms. So focus only on the outer atoms and give each of the outer atom an octet of electrons after connecting with a single bond. See, first you identify the central atom, surround it with the more electronegative atoms, connect each of the outer atom with the central atom with a single bond. After connecting with a single bond, you distribute electrons first to the outer atoms, that is oxygens, hydrogens, chlorines, in such a manner that each one of the outer atoms gets an octet excepting for hydrogen, which will get only a pair. So connect the bonds, connect with single bonds, then give 8 electrons to each of the outer atoms. And the remaining electrons you have to give to the central atom. Central atom should get the last share. Outer atoms should get 8 electrons. 8 electrons means already 2 electrons are used in single bond formation. No? So every one of the outer electrons except hydrogen, every one of the outer atoms except hydrogen should get 6 electrons more. Only the remaining electrons have to come to the central atom. After doing like that, if central atom, whatever leftover electrons you give to the central atom, after doing like that, if the central atom gets 8 electrons or more, it is okay. You are done with the structure. What are the steps? Count the total number of electrons. Compensate for the charge. After compensating for the charge, identify the least electronegative element. Take it as the central atom. Then connect each of the outer atoms with one pair of electrons to the central atom. Then after that, start distributing electrons to the outer atoms. Let each one of the outer atom get 8 electrons each except hydrogen. Give the remaining electrons to the central atom. After giving the remaining electrons to the central atom, if the central atom gets 8 or more electrons, you are done with the structure. You don't have to do anything else. Supposing if the central atom gets less than 8 electrons, but other atoms are from halogen group, that is chlorine, fluorine, bromine, iodine. If the outer atoms are chlorine, bromine, fluorine and iodine, and the central atom is getting less than 8 electrons, then also you are done. If the central atom gets 8 or more electrons, you are done. If the central atom gets less than 8 electrons, but the other atoms are halogens, then also you are done. Then if not, move an electron pair from an outer atom to form a double bond. Supposing everybody got 8 electrons, or hydrogens are there, they got 2 electrons, but central atom is not getting 8 electrons. Outer atoms are not halogens. In that case, you have to convert one lone pair into a pi bond. That is, one pair of electrons on an outer atom has to be converted into a pi bonding pair to the central atom. If not, move an electron pair from an outer atom to form a double bond and get the octet to the central atom. So, you didn't get it even then. Repeat with another atom. You didn't get it. So, you keep on repeating until the central atom also gets an octet of electrons. So, octet is not required if the outer atoms are halogens. That rule is there. But octet is required if the outer atoms are not halogens. You have to convert one lone pair into a pi bonding pair. Even then it is not satisfied, do it with another atom and get the another pair of electrons. So, let us see, let us work with examples for clarity. Lewis structure of CO3 2 minus. As we already calculated, CO3 2 minus is carbon 4, each oxygen is 6, carbon is 4, each oxygen is 6. So, 6 into 3 18 plus 2 total 24 electrons. Then after that you can see here the carbon is less electronegative than oxygen. Draw the skeletal structure. So, our next step is first count electrons, then identify the least electronegative atom, then draw the skeletal structure with the least electronegative atom at the center, other atoms in the periphery. Okay, you did that. Then let us see. You can see carbon here at the center. See, carbon is at the center and 3 oxygens are connected to it through the scale. Why oxygens in the periphery? Because they are more electronegative. Why carbon in the center? Because it is less electronegative. Then we can see 24 minus 6 is equal to 18 more electrons to accommodate. 1 bond means 2 electrons, 3 bonds means 3 into 2, 6 electrons. So, already 6 electrons are over. What is your total count of electrons? Your total count of electrons is 24. Of that 6 you already used for forming bonds. So, how many are left with you? 18. What is the next step? Concentrate on the outer atoms. See that each of the outer atom gets an octet. Outer atom octet can never be violated. So, see that of course, if it is hydrogen, it will get only a pair which is used in bonding itself. So, all others should get an octet. You can see here 3 oxygens are there, 18 electrons are there. So, you will give 6 electrons to each oxygen. You can see here in the structure, each oxygen is having 6 electrons, 3 pairs and 1 bonding pair. So, 1 bonding pair and 3 lone pairs, your 24 count is over. 24 count is over. See, 3 single bonds, 3 into 2, 6. 6 lone pairs of electrons, there are 6 plus 6 plus 6, 18. 18 plus 6 is 24. So, your electron count is over. But are you done with it? You are not yet done. Why? Because how many electrons is carbon having? Tell me. Carbon is not having any lone pair. It is having only 3 bond pairs. 2 plus 2 plus 2 is only 6. So, as far as carbon is concerned, octet is not done. What did we learn? If the outer atoms are halogens, even if the central atom doesn't get an octet, it is fine. but outer atoms are not halogens. So, now you have to adjust the structure such that carbon also gets an octet of electrons. So, now we further modify. So, what did they tell us? Convert a lone pair into a bonding pair such that it will form a pi bond. Convert one lone pair into bond pair so as to form a double bond. You can see here, look here all of you. See, there is one red circle in which that oxygen is having a lone pair. So, that lone pair is converted into a bond pair. You can see here there are two oxygens with a single bond, but there is a third oxygen which is connected to carbon with a double bond. One bond originally we gave in the form of the structure, original structure. The red line is added by converting one lone pair into a bond pair. Now, let us see, convert one lone pair into bond pair. Now, the central atom also has 8 electrons. Count the number of electrons now, all of you. Please count the number of electrons. This oxygen is having 6 plus 2, 8. This oxygen is having 6 plus 2, 8. This oxygen is having 4, but it is having 4 more through bonds. 4 plus 4, 8. Look at the carbon. Carbon is having 2 here, 2 here. 2 plus 2, 4. 4 plus 4 through the double bond, it is having 4 more electrons. So, 8 electrons. Now, everybody is happy because everyone is having an octet of electrons. You can see here, this is the final structure of CO3, 2 minus, where 2 minus is the charge and each of the bonded atoms is having an octet of electrons. So, we have seen with CO3 2 minus how to write the Lewis structure. Let us see the Lewis structure of carbon monoxide. So, carbon is only a diatomic molecule. There is no worry, you do not have to identify the central atom. Carbon monoxide is there. The less electronegative atom, let us concentrate more on the more electronegative atom first. See, we need to give octet electrons to the more electronegative atom first, right? So, first connect carbon and oxygen with a lone pair of, with one pair of electrons, that is one bonding pair, done. So, how many total valence electrons are there in carbon monoxide? Tell me. Carbon is having 2s2, 2p2, that is 4 electrons. Oxygen is having 2s2, 2p4, that is 6 electrons. 6 plus 4 is 10. So, your task is you have to adjust 10 electrons. 2 electrons you already used for forming the single bond. After that, how many electrons you are having? You are having only 8 electrons, but the rule says concentrate on the outer atoms or the more electronegative atom. So, oxygen, we are concentrating on oxygen. We gave 8 electrons to, see here, look here, we gave 8 electrons to oxygen. That means you are left only with 2 more electrons. Those 2 electrons we gave to carbon. So, fine with oxygen because oxygen is having an octet. What about carbon? Carbon is having only 4. So, octet is not complete for carbon. If octet is not complete for carbon, what did the rule say? Convert a lone pair into a bonding pair. Even if you convert one pair also, carbon will get only 6. How many you want? You want 8. So, 2 lone pairs are converted into bonding pairs such that there is a triple bond between carbon and oxygen. Now, see how many electrons carbon is having? 2 plus 6, 8. How many electrons oxygen is having? 2 plus 6. See, when there is a triple bond, it involves 6 electrons. So, 2 lone pair electrons plus 6 bonding pair electrons, total 8 electrons. So, we are done with the carbon monoxide structure. So, that is the Lewis structure of carbon monoxide, in which we adjusted 10 valence electrons with a triple bond between carbon and oxygen and a lone pair each on carbon and oxygen. Now, let us see the next example. The next example is NO3 minus. Now, we have a polyatomic molecule. The earlier one was a diatomic molecule. So, only we took the more electronegative oxygen to complete the octet, and then we focused on carbon. Now, we are having a polyatomic molecule. There are 4 atoms. So, automatically nitrogen will become the central atom because nitrogen is less electronegative. How many electrons to be accommodated? 5 on nitrogen, 6 each on oxygen. So, that is 6 3 is 18, 18 plus 5 23, NO3 minus. So, 24 electrons to be accommodated. First put nitrogen at the center, connect each of the outer atoms with one pair of electrons you connected. Then after that focus always on the outer atoms for filling octet. So, you are focusing on the 3 oxygens, you gave an octet to each one of them. So, how many electrons are accounted for now? So, 8 threes, as you can see here, each oxygen got an octet. Complete the octet and outside atoms. After that, how many electrons nitrogen is having? Nitrogen is having only 6. You want an octet for nitrogen also. So, convert one lone pair into a bond pair. Initially, what was the total count of electrons we had? If you remember, we already calculated it as 24. If I am not wrong, it is 24. 6 3 is 18, 18 plus 5 23, 23 plus 1 24. So, one lone pair is converted into a bonding pair here. So, you can see nitrogen is also now having an octet. This oxygen is having octet, this oxygen is having octet, and this oxygen is also having an octet in the form of 2 lone pair electrons and 2 bonding pair electrons. Now, you can see NO3 minus is the final charge. You can see the final charge is indicated outside of the square bracket. It is the NO3 minus. How to calculate formal charge we will see in the. So, let us see the next example, which is HClO3. Chlorine is the central atom here. Hydrogen cannot be the central atom. Chlorine is the central atom because it is less electronegative than oxygen. You are having a total of 26 electrons to be accommodated. Connect each of the atom with a pair of electrons. You give hydrogen to oxygen with a pair, and the 6 more electrons are used for bonding chlorine with the 3 oxygens. Then after that you give an octet of electrons to the 3 oxygens. Already hydrogen is having 2, it cannot take any more. So, 3 oxygens got 8 electrons each. So, totally 8 3 is 24. You are having 26 electrons. The remaining 2 electrons are given on the chlorine. Why we are converting lone pairs into a bond pair is to reduce the formal charge. That structure which is having maximum number of atoms with 0 formal charge is the most stable structure. So, that is why this conversion is done, which we will see in the later slides. So, here you can see that in this particular structure, hydrogen is having 2, every other atom is having an octet of electrons. Now, let us go. The next example is BF3, PF3 and BRF3. You can see here BF3, boron at the center, 3 fluorines connected to it. Each fluorine is having a lone pair of electrons, not one lone pair. Each of the fluorine is having 3 lone pairs of electrons. Similar is the case with the PF3 atom. You can see number of valence electrons in BF3 is 24. That is 3 plus 7 3 is 21. Each fluorine is having 7. There are 3 fluorines. So, 7 3s are 21 plus 3 24. Phosphorus PF3, phosphorus is having 5. 5 plus 21 is 26. BRF3, then you are having bromine is having 7 and each fluorine is having 7. So, 7 4s 28. So, total 28 valence electrons need to be adjusted. This is the rough skeleton structure. 24 accommodated in each of the above structures. You can see in all these structures 24 electrons are comfortably allotted. How 24? For connecting the 3 bonds, 6 electrons are used. Each fluorine anyhow will get 6 electrons. So, automatically in all these 3 structures, you can see these 3 structures 24 electrons are already accommodated. Then you can see each outer atom got an octet. Fluorine is the outer atom in each of the examples. So, fluorine definitely got an octet. What did the rule say? When the outer atom is a halogen, even if the central atom does not get an octet, it is done. So, in this example, boron is not having an octet, but outer atoms are fluorine, they got an octet, so you are done. Now, come to phosphorus. In phosphorus, how many electrons need to be accommodated? PF3, 26 electrons. How many have you accommodated? Only 24. So, phosphorus is given a lone pair here. Now, phosphorus also is having an octet. So, you are done with the structure. Now, let us see the third example where it is BrF3. BrF3 bromine at the center, 3 fluorines are the outer atoms. Now, after accommodating 24 electrons, you still have 4 more electrons. So, 2 lone pairs are given to the bromine atom, and now bromine is having an expanded octet, greater than octet. Boron is having less than octet. Bromine is having greater than octet. The rule says even if it is greater than octet also, you are done, because bromine got greater than octet and the outer atoms are halogens. You are done with the electron arrangement. So, these are the Lewis structures of BF3, PF3 and BrF3. Boron got less than octet, then even if it is less than octet, because it is fluorine, you are done. And then phosphorus 2 lone pair, that also we discussed. Bromine got an expanded octet. So, these are the examples where the rule is violated. BeCl2. In BeCl2, you can see beryllium is having only 4, but still it is a stable molecule. We thought octet is a condition for stability. There is no octet here, less than octet, but BeCl2 is stable. Similarly, BCl3, boron is having only 6. Of course, outer atoms are having octet, central atom is having only 6, but still it is stable. Then you can see here in the next example, it is an expanded octet, arsenic, selenium, bromine. You can see in these examples, the central atom is having greater than octet. For example, you can see there are 5 bonding pairs around arsenic, which is accounting for 10 electrons. Selenium, it is having 12 electrons. Bromine, it is having 1 lone pair plus 5 bonds. So, it is having many more electrons than the octet. So, these are the examples where molecules are stable, compounds are stable, but the central atom is having either less or more than the octet number of electrons. Now, so far we have learnt to draw the Lewis structures based on a set of rules, and we have also learnt how to arrange the valence electrons around different atoms in the molecule and ion. We stop this lesson here, and in a later part of this lesson, we will learn about computation of formal charge. Thank you. All the images in this video are adapted from open web pages. Thank you.